a past paper on differential equations. We already did a revision on test 1 for 2019. So if you missed that class, then you can just go and watch the video and see what type of questions outside of partial differentiation you can expect. So the test is tomorrow. I'm still waiting for the venues, but as far as I know, it's 12:30 tomorrow. Okay, so before the test tomorrow, I'll let you know where the venues are. So I dropped the test in the chat. You can download it so you can follow along with me, so I don't have to write down the entire questions. So the section in that test on partial differentiation was very short, or it wasn't that much to do, and you can see the type of questions, not particularly difficult. You should be able to do those questions. So we start with question 1.1. We are given some functions r and f, and then we have to work out their first partial derivatives. So this is next version. This is the 2019 test. 1.1.1, we are told that r of pq is equal to tan inverse of pq squared. Now we have to find the partial derivative of r with respect to p, as well as the partial derivative of r with respect to q. So first one. Okay, so we have to use the chain rule. You start the derivative of tan inverse is a fraction. In the numerator, you have the derivative of the inside. So remember, when we're differentiating with respect to p, then it means that q is a constant. So in the numerator, the derivative is q squared. And then in the denominator, we have 1 plus the function squared. So this is 1 plus pq squared squared, which is just q squared over 1 plus p squared q to the power 4. Okay, so that one, pretty simple, nothing too difficult there. Then the partial derivative of r with respect to q. We'll do it in the same way. The derivative of tan inverse in the numerator, you have the derivative of pq squared, which is 2pq. And then in the denominator, you have 1 plus the function squared. So 1 plus pq squared squared, which is 2pq over 1 plus p squared q to the power of 4. Then 1.1.2. Given f, which is a function of x and y, is given by hyperbolic tan of the square root of xy minus ln of the square root of x cubed over y. And we have to differentiate f partially with respect to x and then also partially with respect to y. So we start with df dx. So the derivative of tan, as we know, is sec squared. And then multiply by the derivative of the square root, which is a half xy to the power of minus a half. And then we multiply by the derivative of xy, which is y. So that is the derivative of the hyperbolic tan of the square root of xy. Then we do this one, the derivative of ln, in the same way. So this is minus 1 over the square root of x squared over y, or it's just y over x cubed. So instead of 1 over x cubed over y, you can just invert the fraction inside the square root. And then you multiply by the derivative of the square root, which is a half. And then we have x cubed over y to the power of minus a half. And then you multiply by the derivative of x cubed over y, which is 3x squared over y. Okay, then simplify the fraction as far as possible, or the answer as far as possible. So with the first question, we can see that in the numerator we have y and a sec hyperbolic squared of square root of xy, and in the denominator we have 2 square root of xy. So our derivative is sec squared square root of xy times y then in the denominator we have 2 square root of xy. Then for the second fraction, here this is x cubed over y to the power of half, power of minus half rather. So this square root and this one are exactly the same. So when I multiply them, the square root will cancel. So what I have is minus a half times y over x to the power of 3 times 3x squared over y. Okay, and then we can see what can cancel. The y's can cancel. There's 3 x's here. And there's 2 over there. So there will be 1 left in the denominator. Okay, and then we'll just have 3 over 2. So this x's and then that one will cancel. Okay, so now we just rewrite it nicely. Okay, so that is our answer for the derivative of f with respect to x. Then we do the same thing, the partial derivative of f with respect to y. So this time x is a constant. So the derivative of tan hyperbolic of the square root of xy, this is sec squared of the square root of xy. And then we multiply by the derivative of the square root, excuse me, which is a half xy to the power of minus a half. And then we multiply by the derivative of xy, which is x. So that's the first part of the derivative. And the second part is ln of the square root of x cubed over y. So that's 1 over your square root, which is the same as y over x to the power of 3. And then multiply by the derivative of the square root, which is a half x cubed over y to the power of minus a half. Then you multiply by the derivative of x cubed over y, which is negative x cubed over y squared. Okay, when you've written the derivative out, you simplify it as far as possible. For the first one, we can see in the numerator we have x and sec hyperbolic squared of the square root of xy, and then in the denominator we have 2xy, and the xy is under a square root. So this is x and for the second part, see we have a negative here and a negative there. That will become a plus. And again, when we multiply these two the square roots will cancel, because what is under the square root is exactly the same. So we have plus and half y over x to the power of 3 multiplied by x cubed over y squared. So the x cubed will cancel, and this y will cancel with that one, and you'll be left with 1y over there. So our final answer, x sec hyperbolic squared of the square root of xy, 2 square root of xy plus 1 over 2y. Okay, so this one was a little bit longer than the first question because there's several parts that you have to multiply in the derivative. But again, there isn't anything particularly difficult that was done there. Mm, 1.2 says use implicit differentiation to find dz dx and dz dy. Now the way implicit differentiation works here is exactly the same way it worked when we were talking about full derivatives. So remember that z is a function of x and y. So when you are differentiating with respect to x and you get to a term that includes z, you must write the derivative of z and then also multiply by dz dx. So here our question was y z plus x ln of y is equal to z squared. So we want dz dx. So dz dx, that means only y is a constant, but z is a function of x. So the derivative of this, we don't use the product rule This is a constant multiplying by z. So when you differentiate this with respect to x, you get y dz dx. And then this one over here, we differentiate it, we get ln of y. And then on the other side, the derivative is 2z, and then we multiply by dz dx. So exactly like the way we did implicit differentiation previously. Then you want to collect all the terms with dz dx on one side. You'll factorize and make dz dx the subject of the formula. So we have 2z dz dx minus y dz dx. This is equal to ln of y. So we factor out dz dx. This is 2z minus y is equal to ln of y, and therefore dz dx is equal to ln of y over 2z minus y. Okay, and then we do the same thing to get dz dy. So here, when we're differentiating with respect to y, we have to use the product rule over here because y is a function of y and z is also a function of y. So dz dy, we have the derivative of y is 1, then we multiply that by z the way it is, and then y as it is multiplied by the derivative of z with respect to y. So here, this is just the product rule. Then for the second one here, x ln of y. So here x is a constant, so we just differentiate ln of y, which is 1 over y. So we get x over y. And the same thing we did over here, we differentiate using the chain rule. This is 2z, and then we multiply by dz dy. And then we collect all the terms with dz dy on one side, everything else on the other side. So we have 2z dz dy minus y dz dy, and this is equal to z plus x over y. So on the left hand side, you will factor out dz dy and then make it the subject of the formula. We have dz dy, we factor out, we have 2z minus y, and then on the other side, so we have z plus x over y. Okay, before we divide by this, you may want to combine this as a single fraction. So this is zy, let me write z over y. And this means that dz dy is equal to x plus yz over y 2z minus y. Okay, so that is the partial derivative of z with respect to y. So even if you are not able to make z the subject of the formula and differentiate the way we've been doing, you can still apply the concept of implicit differentiation and work out dz dx and dz dy. Okay, then 1.3. U is equal to e to the power of xy sine of y. Then we have to find uxy as well as uyx. Now we know that those two should end up being the same if we've done it correctly. So you will know if what you've done is correct, and that if your answers are different, then more than likely you did something wrong. Okay, but it's just the order that we do them in that is going to be different. So we first find ux, so that means we differentiate first with respect to x. So when we're differentiating this with respect to x, this means that sine y is a constant, so it's only this part e to the power of xy that we differentiate. So this is y e to the power of xy sine of y. Okay, and now we differentiate this with respect to y. So we have u xy. So this time we will have to use the product rule. So notice here I have three functions. There's the y, e to the power of xy, and then sine y. So if you want to use the product rule, you need to group them. Maybe say the first two is your first function, and then this one here is your second function, and then when you differentiate this one, you have to use the product rule as well. So differentiating the whole thing involves using the product rule, but differentiating this part as well, you have to use the product rule. Okay, so using the product rule,
Yes.
yeah.
Can I use lin?
How?
By adding lin, then separate them.
Yeah, I guess, but will you then be able to make ux the subject of the formula? Let's see, if you take ln of u, I guess there isn't anything wrong if you do it correctly. I don't know if that is necessarily easier. Let me see, you take ln of u. I don't know if that's easier, because when you then you have to use implicit differentiation like we did in the previous one. When you have ln of u, I don't see anything wrong with it, but I think this might be shorter. You can try it and see what your answer will be. Anyway, so product rule over here, we use this one as it is. So I write y e to the power of xy, and then the derivative of sine y. So the derivative of sine y is just cos y, and then I must have the derivative of this one. So the derivative of this one, I'm going to multiply by sine y, so I can just write sine y already. And here I must use the product rule to get its derivative. So the derivative, first, the derivative of y is 1. So it's 1 times e to the power of xy. and then y as it is, and I multiply it by the derivative of e to the power of xy, which is x e to the power of xy. So I'll have I have xy e to the power of xy, like that. And then you can multiply out your brackets, write out uxy. This is y e to the power of xy cos y plus e to the power of xy sine y.
Now, Miss,
Yeah,
I have a question. What if I differentiate everything like at the same time? Like, let's say I differentiate first y, then I maintain the whole thing like e to the power of xy times sine y. Then I differentiate e to the power of xy, then I maintain y and sine y, and then I differentiate sine y, something like that. Is it the
what
same thing?
what rule are you using to get that?
Like I would say product rule, but then considering like three terms in one, something like
Is
that.
that the product rule for 3 terms?
That's my question.
I've never seen that before, and I wouldn't start assuming that. I've never seen a product rule for 3 terms. You could probably come up with one, but I don't think it's as easy as this one. You derivative of this times that, derivative of this times that one. It's not like that. Okay, and okay, so we're multiplying e to the power of xy sine y, and then the last term is, let me just shift all this a little bit up. Okay. E to the power of xy plus, copy it first, plus xy e to the power of xy. Okay. Right. So this one, e to the power of xy sine y, and then the last part is xy e to the power of xy sine y. Okay, let me just see. So we have y e to the power of xy cos y e to the power of xy sine y xy e to the power of xy. Okay, so that is our derivative. Okay, then we have to do it by reversing the order. So that means first we'll differentiate with respect to y, and then after that we will differentiate with respect to x. And remember, we are expecting the same answer that we have over here. If the answers are not the same, more than likely you've done something wrong, because we know that the mixed derivatives are almost always the same, despite of the order you differentiate them in. Okay, so we start with uy. So differentiate u with respect to y. Here we have e to the power of xy times sine y. You must use the product rule here because e to the power of xy is a function of y and sine y is a function of y. So the derivative, I keep e to the power of xy the way it is, and the derivative of sine y is cos y, and then we add, okay, please mute your mic. We add the derivative of e to the power of xy, which is x e to the power of xy, and then we multiply by sine y as it is. Then this is our derivative with respect to y. Now we differentiate with respect to x. So we have u yx. So here, when we're differentiating with respect to x, we don't need the product rule because this one here is a function of y. There's no x. So the derivative of this with, excuse me, with respect to x is just y e to the power of xy, y e to the power of xy cos y. Okay, and then the differentiating this one here, we have to use the product rule, but the product rule is only with that part. So this sine y you treat it as a constant. So you have sine y here, and then the derivative of x e to the power of xy. So first, the derivative of x is 1, then you multiply by e to the power of xy, and then you have x the way it is, and then you multiply by the derivative of e to the power of xy, which is y e to the power of xy. So multiply out our brackets, we have y e to the power of xy cos y plus e to the power of xy sine y plus xy e to the power of xy sine y. Okay, which I believe is the same thing we got over there. So we have y e to the power of xy, then e to the power of xy sine y, then xy e to the power of xy sine y. Okay, so you're sure then that what you've done is correct. So very important that you must have u or uxy equal to uyx, otherwise check your work. Okay, and again with these questions, if you are just given y, find uxy, it might be useful to know that if I differentiate with x first and then with y, it's easier than if I do it in the other way. Okay, so sometimes switching the order is useful because there's less calculations, because in the end you'll get the same answer. And and 1.4, that's the last question, that we have the radius of a circle is increasing at a rate of, sorry, the radius of a right circular cylinder is increasing at a rate of 8 millimeters per second. So we have dr dt. This is positive because it is increasing. So if something is decreasing, then the rate is negative. And the height is decreasing at a rate of 15 millimeters per second. So we have dH dt is negative 15 millimeters per second. So be careful with these rates when it's positive and negative, because that will affect your answer if you make it positive when it should be negative. And then we have to find the rate at which the volume is changing. So we want dV dt, and when or at what instant do we want dV dt? When R is 40 millimeters and the height h is 150 millimeters, and we are told to give our answer in pi centimeters cubed per second. So notice that all our units are in millimeters. So after we have our answer, we still have to convert it to centimeters cubed. And yeah, that is not something you should have a problem with. But here, there isn't much to sketch. You just have your right cylinder. This is your radius, and that is your height. But again, with this question, the sketch is not really needed. Okay, so we just use the total differential equation. Doing that, we know that the volume of a cylinder is given by pi r squared times the height. So if we want dV dt, this is the partial. So here, keep in mind that it is the partial derivative of v with respect to r multiplied by dr dt. So don't make this a full derivative because v has two variables. So if you differentiate with respect to r, it's a partial derivative, not a full derivative. And you add dv dh times dh dt. Okay, substitute whatever it is you have. So dv dr, differentiate with respect to r. This is 2 pi rh. And this will be multiplied by dr dt. And then dv dh, this is pi r squared. And multiply by dh dt. Okay, so now we can just substitute. So when r is 40 and h is 150. Okay, just substituting, we have dv dt. This is 2 pi times r, which is 40, times h, which is 150, times dr dt, which is 8, plus pi r squared is 8 squared. R is 40, sorry. We have 40 squared. And then we multiply by dH dt, which is minus 15. So you can see that if I had put a positive 15 over here, it will obviously give me a different answer. So this you just type in on your calculator. It says we must leave it in terms of pi. So this is 72,000 pi, but this is millimeters cubed per second. The question says leave it in centimeters cubed per second. So converting millimeters squared per second, you just divide by 1,000. So this is 72 pi centimeters cubed per second. Then you can say, answer the question. What does the question say? It says find the rate at which the volume is changing. Say the volume is changing at a rate of 72 pi centimeters squared per second. And that's it. So you can see again, as long as you understand the wording in the question, you use the formulas correctly, you will not have any problems. So this was a paper set by Mr. TK, so it's not, I think he's going to keep it at the same standard. It's not going to be a very difficult test. If it's a 90-minute paper, you should be done. And yeah, that's it. So we'll stop here for today unless there are any questions. But like I said, I still don't know the venues